This is your presenter Asloob Mudassar, and I am presenting part E of slide number 142. It is required that you go through previous slides, that is part A, part B, part C, part D of slide number 142, so that you can easily comprehend this slide or this presentation. In this presentation, I am going to present erbium YAG laser, erbium glass laser, tholium, holmium YAG laser, and these will be presented in brief. So erbium glass, erbium YAG, and erbium glass lasers. Let's first talk about the erbium YAG laser. In erbium YAG lasers, it 10 to 50% of the yttrium ion, that is Y3 plus ions, are the ions of these positions are occupied by the erbium 3 plus ions, that is the erbium triply ionized ions. Relevant energy levels of the erbium YAG laser are shown in part A of figure number 4. So let me show you that figure first. This is the figure. Let's read the caption. Relevant energy levels of the erbium YAG laser in part A, and erbium phosphate in part B. So let's talk about part A. That is the erbium YAG laser. And you can see that these are the levels in which the erbium is splitted. 4I15 is the ground level. The higher levels are 4I13 half, 4I11 half, and 4I9 half. The two main laser transitions have been shown. One is at 2.94 micron from the level 4I11 half to 4I13 half. And the second transition that is shown is 1.64 micron from the level 4I13 half to the ground level, which is 4I15 half. So these are the two possible transitions of giving laser wavelengths at these two transitions. There is an up conversion is also shown. That is when the concentration of the erbium ion is increased, then up conversion will occur from the level of 4I13 half to the level 4I9 half. And this is for the continuous operation. For the continuous operation, as we shall see through following some paragraphs, we shall see that this up conversion is required in the continuous operation from the erbium YAG laser. But if the pulsed operation is required, then the transition from 4I11 half to 4I13 half is required, and the second transition is from 4I13 half to 4I15 half. Here 4 is actually the multiplicity of these levels, which is 4. And of course 9 half, 11 half, 13 half, and 15 half is the total quantum number of the system. Okay, the relevant energy levels of the erbium YAG laser are shown in part A of figure 4, which I just explained. Two important transitions are 4I11 half to 4I13 half at a wavelength of 2.94 micron, and the second at 4I13 half to 4I15 half at a wavelength of 1.64 micron. So let me show you again these two transitions that I am talking about. 4I11 half to 4I13 half at 2.94 micron, and the second transition, that is the second laser transition, is from 4I13 half to 4I15 half, which is at 1.64 micron. In the excitation of upper laser level, that is 4I11 half, is possible through flash lamps with a wavelength less than equal to 600 nanometer are absorbed efficiently. So you see that here we are talking about the level 4I11 half, and this is here the 4I11 half, this level. So the pumping to this level can be done efficiently. So in the excitation of the upper laser level, which is 4i11 half, by the pumping is done by flash lamps at a wavelength less than equal to 600 nanometer. And this flash lamp pumping is absorbed efficiently, whereas the pumping by diode laser is done at a wavelength of 970 nanometer using indium gallium arsenide or gallium arsenide quantum well-strained lasers. So two options are available for the pumping mechanism, which we just discussed. The lifetime of the level 4i11 half is approximately zero point 0.1 millisecond, whereas the lifetime of the level 4i13 half is approximately 2 millisecond. Thus, the lasing action for the transition from 4i11 half to 4i13 half is pulsed, because the lower laser level has a more lifetime. So that's why the pulsed operation is possible between these two levels. If CW operation is required, diode lasers must be used as a pumping source with the high concentration of erbium in the erbium YAG. In high concentration material, the strong erbium ion to erbium ion interactions, that is Er3 plus to Er3 plus interactions, lead to an efficient up conversion, that is 4i13 half to 4i9 half. So this is up conversion is possible when high concentration is present and the pumping is done through diode lasers. That is the pumping from a lower laser level to the upper laser level indirectly. So you see that the up conversion has been shown from the level 4i13 half to the level 4i9 half, and this is only possible when there is a significant or increased addition of the erbium ions to the YAG crystal. Typical size of the erbium YAG rod is 6 mm in diameter and 7.5 centimeter in length. Flash lamp pumping is done in elliptical cylindrical geometry. Such a system gives output energy up to 1 joule with a repetition rate of up to 10 Hz. Erbium YAG at a wavelength of 2.94 micron is very useful in biomedical applications due to its high absorption in water. So this was a brief introduction about the erbium YAG laser. Next, we are going to discuss the erbium phosphate lasers. So in erbium phosphate lasers, the concentration of erbium is kept low to avoid any up conversion as indicated for the erbium YAG laser in part A. So you see that you can see that this is up conversion, and this is due to the increased mixing of erbium ion. So you see that if we want to use less concentration of the erbium ion, then of course this up conversion will not be possible, because we want to avoid this up conversion. So the ultimate solution of avoiding this one is that we add some ytterbium concentration. So let's read about this. Relevant energy levels of the erbium phosphate is shown in part number B. The laser transition from 4i13 half to 4i15 half gives lambda is equal to 1.54 micron. You can see this transition which occurs in the erbium, that is 4i13 half to 4i15 half, is done at 1.54 micron. And here alongside I have shown the two levels of the ytterbium ion. One, the ground state is 2f7 half, and the upper excited state is 2f5 half. And the pumping is done at a 980 nanometer wavelength from the ground state of the ytterbium to its excited state, and then this energy that is this level will transfer its energy to the 4I11 half level through dipole-dipole interaction. So this energy from the 2F5 half is transferred to 4I11 half, and then from 4I11 half the transition takes place to 4I13 half, and then from 4I13 half to 4I15 half a laser transition occurs at 1.54 micron. The laser transition from 4I13 half to 4I15 half gives lambda at 1.54 micron. The absorption cross section for lambda is equal to 1.54. That is to the level 4I11 half is quite low. So if we want to have an excitation from the ground state of erbium, that is 4I15 half to 4I11 half, then the cross section for this transition is very weak. So this transition, that is from 4I15 half to 4I11 half, is a weak transition. So this transition is not is very weak. So that's why we have added ytterbium ion, so that we can raise the population to the 2F5 half level, and from there the transition from there the energy is transferred to 4I11 half through dipole-dipole interactions. So that so this transition will occur between from 2F5 half to 4I11 half through dipole-dipole interactions, and 4I11 half will get populated. So the absorption cross section for the wavelength lambda is equal to 1.54, that is to the level 4I11 half is quite low. Ytterbium ion, triply ionized ion, or ytterbium 3 plus, is doped along with the erbium to increase the population to 4I11 half. The level 2F5 half of the ytterbium lies closely to the 4I11 half level. 2F5 half is pumped using a continuous wave diode laser at a wavelength of 980 nanometer through the transition from 2F7 half to 2F5 half. So the transition from the ytterbium at a level from the level of 2F7 half to 2F5 half is done using CW diode laser at a wavelength of 980 nanometer. The transfer of excitation from 2F5 half to 4I11 half takes place through the dipole-dipole interaction. So the transfer of excitation from 2F5 half to 4I11 half is done through the dipole-dipole interaction. The level 4I11 half then decays very rapidly to the upper laser level 4I13 half in a time span shorter than 0.1 millisecond. That is from 4I11 half. The transition takes place very quickly to the 4I13 half. And then the population gathers at the 4I13 half, which forms and then the inversion is achieved for this level, which is 4I13 half. So the level 4I11 half then decays very rapidly to the upper laser level 4I13 half in a time span shorter than 0.1 millisecond, that is through multiphonon relaxation. The lifetime of the upper laser level, which is 4I13 half, when erbium doped in the glass, is quite long, of the order of 8 millisecond. So you see that the lifetime of this level is quite high, of the order of 8 millisecond. Thus the upper laser level 4I13 half and the lower laser level 4I15 half are suitable for laser action. The terbium glass can also be pumped using flash pumps, using flash lamps. This laser behaves purely as a three-level laser system. Application area includes optical communication in fiber and in free space and in other optical measurements. The wavelength 1.54 micron is safe for human eye. The next laser that we are going to describe is the holmium YAG laser. So in the YAG crystal, we have contributions from the holmium and from the tholium. In this laser, some ions of the aluminium 3 plus, that is the triply ionized aluminium ions in the YAG crystal, are substituted by the tholium ions, that is tholium triply ionized ions, simply called tholium ions, and the holmium triply ionized ion, which we simply call as holmium ions. The 3H4 level of the tholium is either pumped directly by the aluminium gallium diode laser at a wavelength of 785 nanometer longitudinally, or by flash lamps in the form of elliptical cylindrical cylinder when the active medium is in the form of a rod. The pumping is done from the ground state of the tholium ion, which is a 3H6 level. So let me show you these levels. So the caption of the figure is a simplified energy level diagram of the chromium, tholium, holmium YAG laser. So far let's talk about first the tholium ion, the levels due to the tholium ions. You can see that here I have shown the levels in this part, and these levels have been labeled as a 3H6 level, which forms the ground state level of the tholium ion. Then the next higher level is 3F4, and the next to that one is 3H4. So these three levels are important for our description of the laser. So that's why I have mentioned only these three levels. 3H6 as the ground state level. The next high levels are a 3F4 and a 3H4. These are the three levels due to the tholium ionized, due to the tholium triply ionized ion. So I have mentioned over here two levels. The 3H4 level of the tholium ion is either pumped directly by the aluminium gallium diode laser using a wavelength of 785 nanometer longitudinally, or by flash lamps in the form of elliptical cylinder when the active medium is in the form of a rod. Pumping is done through the ground level of the tholium ion, which the level has been marked as 3H6 level. There is a radiative decay from the level 3H4 to the level 3H6. So you see that when the pumping is done from the ground state level of the tholium, that is from 3H6 to 3H4, then the transition can occur backward, that is from 3H4 to the 3H6 transition is also possible radiatively. And then of course that will be a useless practice. So because we want to obtain the transition from 3F4 to 3H6, so we want to attain the population inversion for the level 3F4, not for a 3H4. So 3F4 is the level that we want to have a population inversion for this level. So there is a radiative decay from the level 3H4 to the level 3H6, which is not required. To minimize this decay concentration of the tholium ion, the tholium is kept high in concentration of the order of 10%, under which the cross-section cross-relaxation process due to Foster type ion-ion interaction between the adjacent ions result in the de-excitation of one thallium ion in the state 3H4 into two excited thallium ions in the state 3F4, which is expressed as. And you know that this is through the cross relaxation process. So what we do is that in order to avoid the transition from 3H4 back to 3H6, we increase the population, we increase the contribution of this thallium ion, and then due to the interaction between the two ions, that is the Foster type interaction between the two nearby thallium ions. What happens is that the cross relaxation process takes place, and what happens in that, this 3H4 will will be relaxed to the 3F4 level, and the rest of the energy will be given to 3H6, and the 3H6 will be raised to 3F4 levels. So this 3H4 level will decay to 3F4 level, and at the same time the energy difference will take 3H6 to the level 3F4. And this transition can be shown in the form of this reaction, that is the thallium ion in the state 3H4 plus the second thallium ion in the state 3H6 through the cross relaxation process will produce two thallium ion in the state 3F4. That the thallium ion in 3H4 state under the Foster type ion interaction reach to an excitation level of 5I7 of the holmium ion. So you see that now we have the holmium over here. We have also a concentration of the holmium here. And then you see that when 3F4 gets populated, which is shown over here, the one population, so this level 3F4 will transfer its energy to the 5I7 level of the holmium ion. So the energy from the thallium ion in the state 3F4 is transferred to the 5I7 level of the holmium ion, because these ions are very close to each other in energy. So the transfer of energy will take place to the 5I7, which forms the upper laser level of the holmium ion, whereas the ground state corresponding to the holmium ion is 5I8. So the transition will from the upper laser level of 5I7 to the ground laser level 5I8 will occur for the holmium ion, and with an emission of 2090 nanometer wavelengths. So you see that in this process we can also excite the 3F4 level using the pumping mechanism, and using a wavelength of 2013 nanometer can be used to raise the thallium ion from its ground state 3H6 to its first excited state, which is 3F4, as shown over here. And then this will transfer its energy to the 5I7, which is the upper laser level of the holmium ion. So the transition from the upper laser level 5I7 will occur to 5I8, giving you a laser wavelength at 2090, that is 2090 nanometers. So let me read this paragraph. The thallium ions in 3H4 state under the Foster type ion interaction reach to an excitation level of 5I7 of the holmium ion. So you see that this 3H4 and the ground state, which I have shown over here, you see that the two will produce two thallium ions in the state 3F4, and then the thallium will transfer its energy to the holmium ion, to the 5I7 level of the holmium ion. The laser action occurs between the lowest sublevels of the 5I7. So you see that 5i7 have 5i7 manifold has many sub-levels, and the laser action occurs between the lowest sublevel of the 5i7 manifold of holmium ion to a sublevel of 5i8 manifold of the holmium 3 plus ion of the holmium ion, which is nearly 462 centimeter above the ground sublevels of 5i8 manifold. That is the transition from 5i7 to 5i8 will give you lambda at 2090 nanometers. So this level, which is a 5i7 manifold level, contains many sublevels, and the transition from these sublevels will take place from the lowest sublevel of this manifold to to a level of 5i8 manifolds. So 5i8 manifolds also has many levels, and the transition will occur from the lowest sublevel of 5i7 manifold to a level of 5i8 manifold. Okay, the laser action occurs between the lowest sublevel of the 5i7 manifold of the holmium ion to a sublevel of the 5i8 manifold of the holmium ion nearly, which is at 462 centimeter above the ground sublevels of 5i8 manifold. So you see that the lowest, since there are many levels present in the 5i8 manifold, and the transition, laser transition that will occur to that transition to a sub level of 5i8 manifold, that level exists at a level of 462 centimeter inverse above the minimum sub level of the holmium ion in the manifold of 5i8. So the transition from 5i7 to 5i8 gives you a wavelength of 2090 nanometer. The active medium is normally cooled down below minus 10 degrees Celsius to reduce thermal population in the lower laser level. The system thus behaves as a quasi three-level laser system. In the absence of the holmium doping, the laser transition occurs between 3F4 and 3H6 levels. That is the transition from 3F4 of the thallium ion to 3H6 of the ground state of the thallium ion, giving you thallium ion, giving you a wavelength of 2013 nanometer. So you see that this is also shown over here. That is the transition from 3F4 to 3H6 levels of the thallium ion, giving you a wavelength of 2013 nanometers. If the holmium is not present, then this transition at a wavelength of 2013 nanometer can also be produced. For efficient flash pumping, chromium is doped, replacing some aluminium ions in the YAG crystal. The two transitions from the ground state of 4A2 to the higher levels of 4T2 and 4T1 are pumped. That is, the chromium ion is excited to 4T1 and 4T2 through the transitions from its ground state 4A2 to 4T2 and 4A2 to 4T1. So now let me show you the chromium ion, the energy levels corresponding to the chromium ion. 4A2 is the ground state of the chromium ion, and the higher excited states are 2E and 4T2 and 4T1. So the pumping is done from its ground state of the chromium ion, which is 4A2, to the 4T1 level and the 4T2 manifolds. So so the pumping is done from 4A2 to these absorption bands, that is 4T1 band and 4T2 bands. And from that one, the energy is transferred to the level 3H4. And this is only done when the holmium is not present. Or even if the holmium is present, then of course, in order to increase the population in the level 3H4, the chromium is added. So the excitation energy is then effectively transferred to 3H4 level of the thorium ions. So of course, you see that I have shown that the energy is efficiently transferred from these absorption bands to the level 3H4 of the thorium ion. So a large population gathers at in the 3H4 manifolds. This increases the population in the level 3F4 and consequently increases the population in the upper laser level. So you see that when we are just only talking about the thorium, then the upper laser level will be 3F4. And since a large number of population has gathered over there, this population will be transferred to this level, which is a 3F4 level, which forms the upper laser level for the thorium ion. And then the transition will occur from this 3F4 level to the 3H6 level, giving you an emission of a wavelength at 2030 nanometers. The holmium concentration is typically less than 1%. Simplified energy level diagrams of the chromium, holmium, YAG laser is shown in figure number 5, which I have explained. So you see that this is the figure which I have explained. The labeling of the chromium ion levels follow from the group theory. With flash lamp pumping, the active medium is in the form of a cylindrical rod with flash lamps arranged in elliptical cylinders. The typical dimensions of the rod are diameter from 5 to 6 millimeter. The length is from 7 to 8 centimeter. Such a system gives energies greater than 1 joule in a 200 microsecond long pulses, repetition rate not exceeding 10 hertz, and a slope efficiency below 4%. Application area includes laser radar systems for wind velocity measurement and the treatment of biomedical tissues which have very good absorption around 2 micron wavelength. Use of this wavelength is eye safe. So this was all about the laser that I have just presented. That is the chromium, thorium, holmium YAG laser. And this is the end of part E of slide number 142.